Another very prevalent type of motion in our daily life is motion down an incline, and because it's the motion down an incline is governed by gravity, it also can we can also apply our kinematic equations for constant acceleration. So let's try and figure out how that works. If we have an incline that is inclined an angle theta, okay, that means an angle theta above the horizontal. It's the angle of inclination. And we have an object that is free to slide down that incline, then gravity, which is pointing straight down, will have a part that pulls it down the incline. The other part is pulling it into the incline and does nothing, since the incline is constraining it to move only along this line. Now, though this is technically a two-dimensional problem in the sense that we have both vertical motion, the box is decreasing its height, and horizontal motion, it's moving to the right here, it technically and mathematically is actually just a one-dimensional problem. The motion constrained by the incline, this ramp, is moving along a straight line. And so we can actually choose a coordinate system that points along that motion and thereby define or have a one-dimensional problem. So I can choose this to be the x direction if I want. And my goal is to find the acceleration in that direction. I know that the acceleration due to gravity is 9.8 meters per second, but that's straight down. How much of that is pulling it down the ramp? Okay, so if I take this and look at it a little further over here, we can break this gravitational acceleration into two pieces. One that points down the ramp and one that points perpendicular to the ramp. Generically, I like to call this A parallel. It's the one that's parallel to the ramp, the one of interest. And the one pointing into the ramp I'll call A perpendicular, and we don't really care about that one because it's not affecting anything because the ramp is constraining it. Okay, and there's a relationship by the fact that this is a right triangle. These two come together at right angles to relate this side to G. Now, it might not be obvious from the geometry here, but I'll leave to you to explore that. But the angle theta, if it's measured up from the horizontal for our physical picture, is opposite this parallel acceleration in this diagram here, which says that if G is the hypotenuse and A parallel is the opposite side, that sine of our angle of inclination is equal to our acceleration parallel to the ramp divided by G, the hypotenuse, opposite over J, or hypotenuse, which means the acceleration we care about is equal to G sine of theta. That is still a constant, because as long as our ramp isn't changing its angle, which for a straight ramp, that's what we'll choose, sine of theta is a constant, G sine of theta is a constant, so we have a new constant acceleration and can do the same type of problems down this ramp. We can choose an initial position, a final position, we can have an initial velocity, a final velocity, and we now know our acceleration down that ramp, and we could solve for some unknowns. How long does it take to go down, for example?